Welcome to this explainer. Today, we're tackling one of the most polarizing, complex, and genuinely fascinating subjects in the entire world of energy. Okay, let's dive into this. We are putting a magnifying glass on the massive paradox that is nuclear energy. On one side, you've got the incredible promise of highly reliable, zero-carbon power. But on the exact opposite side, there's the heavy burden of literally million-year risks. Think about this, a 92% capacity factor and zero direct CO2 emissions. That means nuclear energy is unbelievably reliable, right? It runs almost constantly, day and night, without pumping greenhouse gases into our atmosphere. But right next to that amazing promise, we face a pretty terrifying catch. The radioactive waste it produces remains hazardous for hundreds of thousands of years. It is the ultimate paradox. Is nuclear energy the essential key to a clean climate future, or is it just an unacceptable risk? To really understand this debate, we've got to look at the facts impartially. So here's our roadmap for today. We'll look at the nuclear energy paradox, break down the physics of fission, see how we actually harness that energy, tackle the long waste problem, objectively compare Chernobyl and Fukushima, and finally, evaluate the ultimate climate trade-off. All right, let's start with the physics of fission. Before we can even begin to debate energy policy or analyze these big disasters, we have to zoom way in, right down to the microscopic world of atomic energy. Grounding ourselves in the objective science just makes the whole picture so much clearer. So what exactly is nuclear fission? Well, it's the literal splitting of a heavy atomic nucleus. In most commercial reactors, the fuel of choice is a specific isotope called uranium-235. When this nucleus absorbs a slow-moving neutron, boom, it splits apart. It releases two smaller nuclei, 2 to 3 new neutrons, and a massive burst of energy. We're talking about 200 mega-electron volts here. Let's move to and see how this builds, because it's not just a single split, it's a precisely engineered sequence. First, a slow neutron is absorbed by uranium-235. Then, that nucleus briefly becomes unstable uranium-236. Step 3, it immediately splits into fission products, kicking out those new neutrons and energy we just talked about. And finally, step 4, those newly released neutrons go right on to trigger nearby uranium-235 nuclei. This creates a continuous, self-sustaining loop. The sheer scale of this energy is completely mind-boggling. 50 million. A single nuclear fission event releases about 50 million times more energy per atom than a standard chemical combustion reaction. Like burning a piece of coal or natural gas. That is a staggering amount of power derived from an incredibly, unbelievably tiny mass of fuel. But obviously, all that power needs strict control. The goal of a nuclear power plant is not a rapidly growing explosive chain reaction. That's the condition for a bomb. Instead, engineers meticulously design these reactors to keep what's called the multiplication factor, or K, precisely at 1.0. Think of it like a Goldilocks zone. Not a dying ember, and definitely not an uncontrollable explosion. By using absorbing rods and moderating materials, the reactor maintains a perfectly balanced, steady chain reaction. On average, only one neutron from each fission goes on to cause exactly one more fission. Which brings us to harnessing that energy. Now that we've got a handle on the microscopic atomic science, we need to scale up to the massive industrial machines humans have built to harness and control this immense power. And this brilliantly illustrates the top commercial reactor designs out there. Engineers globally rely on a few incredible machines. The most common one you'll see worldwide is the pressurized water reactor, or PWR. It uses water under extreme pressure as both a coolant and a moderator, along with enriched uranium. Then you have boiling water reactors. Here, the water boils directly to generate the steam that actually spins the turbines. And finally, can-do reactors, which uniquely use heavy water, allowing them to actually run on natural, unenriched uranium. You might also hear about breeder reactors in this space. This is an absolutely amazing concept that uses fast neutrons to convert non-fissile uranium-238 into fissile plutonium-239. It actually creates more fissile material than it consumes, literally making more fuel. Theoretically, this could extend our global uranium supplies enormously. But in practice, they are extremely expensive and technically super difficult to build, so very few operate globally today. Moving right along to the long waste problem. Now, this is where we shift to the consequences of harnessing all that power. Because after about 3 to 4 years, the fuel rods lose efficiency and are taken out of the reactor. But the story of that nuclear material, it is far from over. A very, very long radioactive hangover is just beginning. To grasp why this waste is such a profound problem, we have to understand the concept of half-life. It's simply the time required for half of a given radioactive isotope to decay. Spent nuclear fuel contains elements like plutonium-239, which has a half-life of over 24,000 years. Because of these incredibly long half-lives, this spent fuel isn't just a problem for our kids, it's an intense, penetrating radiological hazard for up to 1 million years. It demands isolation on a literal geological timescale. The timeline of nuclear waste is just staggering. The fuel spends 3 to 4 years inside the active reactor core. Once removed, it spends 5 to 10 years cooling down in massive, water-filled pools on site. After that, for decades, it just sits in dry cask concrete and steel storage containers. The final step is supposed to be a deep geological repository for 100,000 plus years. But right now, mostly due to political realities, the U.S. relies entirely on those temporary on-site pools and casks, simply because the planned federal repository at Yucca Mountain was halted by Congress. Actually, right now, Finland is the only country in the entire world actively constructing a permanent deep repository.
Let's look at what happens when things go wrong. Chernobyl versus Fukushima. We absolutely must look at what happens when that delicate balance of fission fails if we want to understand the true risks of this technology. When we neutrally analyze the two most infamous disasters in history, a pretty stark contrast emerges. At Chernobyl in 1986, the catastrophe was driven by a fundamentally flawed Soviet reactor design, coupled with severe procedural violations during a safety test. Fukushima in 2011, however, was triggered by a massive external natural hazard, a 9.0 earthquake and a tsunami that completely exceeded the plant's design limits. Both events tragically resulted in severe core damage and massive exclusion zones, but their underlying mechanisms were entirely different.
The Chernobyl cascade started with operators violating safety protocols. But the fatal engineering flaw was the reactor's positive void coefficient. What does that mean? Well, it meant that as cooling water turned to steam, creating empty voids, the reactor's power actually increased, which is the exact opposite of a safe, water-moderated design. Combined with control rods that had graphite tips that briefly spiked the reaction when first inserted, the result was a massive, uncontrollable power surge. We're talking 30,000 times normal operating levels in a fraction of a second. This caused a catastrophic steam explosion and a raging graphite fire. Yet, surprisingly, the aftermath presents an unexpected ecological reality. The 1,000 square kilometer exclusion zone around Chernobyl has actually become an unplanned wildlife refuge. Without human activity around, large mammals like wolves, lynx, and wild horses have returned in massive numbers. It illustrates a really provocative point. Chronic low-level radiation might actually impose fewer ecological costs than direct habitat destruction by humans. It's a fascinating and sobering reminder of humanity's footprint.
Now, what's really interesting about this slide is how Fukushima's cascade fundamentally contrasts with Chernobyl. It was not an uncontrolled power surge. It began when a massive 9.0 earthquake triggered a devastating 14-meter tsunami wave that completely overtopped the plant's 5.7-meter seawall. The reactors actually shut down safely, but the flooding destroyed the backup diesel generators. With a total loss of power, there was a total loss of cooling to 3 reactor cores. The residual decay heat caused the cores to melt down, leading to a dangerous buildup of hydrogen gas and subsequent explosions.
Finally, let's talk about the ultimate climate trade-off. Let's zoom all the way out from the disasters and the microscopic science to synthesize the overarching meta-debate surrounding global energy policy today. Because this is the ultimate dilemma. On one hand, we have incredible benefits, a 92% capacity factor, meaning reliable baseline power, and near-zero life-cycle greenhouse gas emissions. In fact, estimates show nuclear has lower emissions than even solar panels. But weighing against that is the massive burden of the long-term waste hazard, requiring perfect isolation for up to 1 million years, plus that finite risk of catastrophic failure we just explored. So, the crucial point is, whether this trade-off is acceptable really depends on how we weigh near-term climate benefits against low-probability, long-consequence outcomes. It is an incredibly complex balance. We are facing a quintessential environmental risk assessment that physics and engineering alone simply cannot resolve for us. Which leaves us with a pretty provocative question. What trade-offs are we willing to accept for our climate future? As we strive to build a zero-carbon world, do the immense, reliable benefits of nuclear power outweigh the million-year peril of its waste and the severe risks of a disaster? It's a debate that requires a clear, objective understanding of the facts, and I really hope this explainer has empowered you to weigh them for yourself. Keep learning, keep questioning, and I'll catch you on the next explainer.